Hi everyone, this is lecture video 25. We will cover graphical behavioral functions from derivatives in this lecture video. Look at the first figure. You will see a very nice function which is continuous everywhere and differentiable everywhere, right? This is continuous because there is no breaks, no jumps at this graph, right? It is differentiable because there are no corners, no cusps, no wild oscillation behaviors. So it is a very nice, smooth, connected graph, and it rises sometimes like this and it falls sometimes. Okay, look at the second one. Here you see an increasing function. This is an increasing function because the images are always getting bigger. That's why the first derivative of this function is always positive. Okay, first derivative is always positive. This function, on the other hand, is a decreasing function. It is always decreasing, meaning that the first derivative function will always be negative. Okay, so like this. In the next figure, we will analyze the second derivative. So this is an increasing graph. First derivative is positive. We already talked about this. This is an increasing function, first derivative positive. Also, you see a concave up shape here, right? This curve is concave up, meaning that second derivative is positive. Okay, so in this picture, you see an increasing concave up function. And here, this is a decreasing graph. It is still concave up, okay? Still concave up. So second derivative is positive for both. The only difference is first one is an increasing concave up function. Second one is a decreasing concave up curve. And here, similarly, when second derivative is negative, you will have a concave down shape, right? In the first one, you see an increasing concave down graph. In the second one, you see a decreasing concave down function. Okay, so let's summarize what we have just told. Okay, if first derivative is positive, your function is increasing. If first derivative is negative, your function is decreasing. What about the second derivative? If second derivative is positive, your function is concave up. If second derivative is negative, your function is a concave down function, just like we see here. Okay, look at this figure now. Here, before this point, this is a concave up shape, right? Concave up. That's why second derivative is positive before this point. And after that point, you obtain a concave down shape, meaning that second derivative will be negative. Since at this point, second derivative changes its sign, this point is called an inflection point. Okay, so let me also put some words about inflection point here. If second derivative is 0 or it may fail to exist, for example, or fails to exist at some point, may also indicate point information. So if this is 0 or if this thing is undefined, fails to exist, then x equals c is a candidate for an inflection point. To verify whether it is in fact an inflection point or not, you will look at whether the second derivative changes its sign at x equals c or not. So you will quickly look at the second derivative, whether it changes sign or not at the point c. Okay, it may happen that first derivative is just like here, positive before the point, and After that, it may be negative, or it may be negative first, then positive. So you see, if these two are the cases where concavity changes, so if second derivative positive, concave up, concave down, down, up, you know. So concavity changes. In other words, second derivative changes its sign. If this is the case, then you can now call x equals c as an inflection point, okay? Inflection point. Okay. So inflection point is the point where the concavity changes or where the second derivative changes its sign. This is how you should check whether a point is an inflection point or not. Okay, so here. Okay, next, look at this part. Over this graph, at this point, what do we have? We have a horizontal tangent, right? And horizontal tangent means that the first derivative is 0 there. And before this point, since your function is increasing, you know, it's an increasing function, after that point, your function starts decreasing. And increasing means first derivative is positive, decreasing means first derivative is negative. So that's why your function behaves like this. First increasing, then starts decreasing. And right at this point now, you have a local maximum point, right? So this point is local maximum point. When do we have local minimums? First of all, you need to have something like, first derivative is 0, and then to detect whether this point C is a local max or local min, you will create a sign table. Before this point, your function is decreasing, so first derivative is negative. After that, it is an increasing function, meaning that first derivative is positive, so that your graph makes this kind of behavior. That's why right at this point, you have a local min, in this case, local minimum point. So this is called as first derivative test to detect local max min points. First derivative test. Okay, let me put some words about first derivative test to here. If your first derivative is 0, or it may happen that first derivative is undefined. Remember, we call such points as critical points of the function. If these two cases happen at some particular point, x equals c, then x equals c is now a candidate for an extremum, local extremum point. Okay, how can we verify whether it is a local max or local min? Okay, so to verify that, just like we did here for the inflection point, you need to verify whether the first derivative changes its sign or not, okay? So at the point C, for the point C, you will create a sign table for the first derivative. It may happen that it is okay, let's go in this order. So if your function is increasing before C and decreasing after C, what happens then? Your function is doing this and doing this decreasing behavior. So at this point, x equals C, you have obviously a local maximum point, right? So here C is a local max. If this is the case, if first derivative changes its sign from positive to negative. What if the first derivative function changes its sign from negative to positive? Then about the original function, you can say that since first derivative negative, it is decreasing, then it is increasing. And this point, local minimum occurs, okay? So to detect local max or minimum points, first of all, you will compute the first derivative and try to see at which points first derivative is 0 or undefined. These two, both of them may happen. And if, for example, undefined, you will have such kind of things there, okay? Corners or cusps. But they are both local max or local min. Okay, so if one of them happens, then this point is a candidate for a local max or min. To prove or to make sure that it's a local min or max, you need to check whether the first derivative changes its sign or not. If it changes sign from positive to negative, it is obviously local max. If negative to positive, it will become like that, so it is a local minimum point. If first derivative doesn't change its sign, this may also happen. Even if the first derivative is 0 there, your function doesn't have a local max or local minimum point at C. For example, it may happen like this, right? So here you have a horizontal tangent, but okay, f prime C is 0, but there is no local max or minimum point here because first derivative is, your function is increasing, still increasing. First derivative is always plus before and after the point C. Okay, so let's also put this case here. It may happen that it is plus plus, or sometimes it may happen like minus minus. Even if your first derivative is 0 at C point, you don't have local max or minimum points there. No local max or min. You see? So this means what? If first derivative is 0, you cannot directly say that the point C is a local max or min, okay? Because it directly depends on whether your function first derivative function changes its sign or not. If it changes sign from positive to negative, local maximum occurs, negative to positive, local minimum occurs. If it does not change its sign, as you can see in this figure, or in this figure, like here, there is no local max or local minimum points. F prime is negative, F prime is still negative, doesn't change sign, no local max min point. Also here. Okay, so this summarizes lots of things for you. And let's look at last two things. If you have first derivative 0, meaning that there is a horizontal tangent. And in addition, if your second derivative is less than 0, meaning that your function is concave down. So you need to draw this kind of shape, right? That's why there is a local maximum point there, okay? Local max. And similarly, if first derivative 0, meaning that you have a horizontal tangent at this point, if second derivative is positive, meaning that you need to draw a concave up shape like this, then at this point, a local minimum occurs, right? And this is also a way of detecting local extremum points like local max, local min. We were also detecting local max min in the previous case where we call it as the first derivative test. There is also this way of detecting them, which we call as the second derivative test, okay? This is second derivative test. All those things that I explained over this diagram is covered before. So I think this is a very nice summary for you of the content that we have covered in the last two lecture videos. So I stop here. Thank you for your attention.